In this video, we will be looking at finite differences. So we're going to start off with a few table of values. In our first table of values, it will be for the function y equals x cubed. So let's start by filling in the y values. I've selected some x's for us from -3 to 4, and we're going to take each of those x's and raise them to the power of 3. So -3 all to the power of 3 is -27. -2 all to the power of 3 is -8. So continue with your table of values and then come back to the video so that we can go on to our differences. Now that we have our y values, we can start with our first differences, like in grade 9. Your first differences, or any differences for that matter, you're taking the consecutive y values and subtracting them, but just keep in mind, the bottom value subtract the top value. So I'm going to go from the bottom of my table, and I'm going to do 64 minus 27 is 37. 27 minus 8 is 19. 8 minus 1 is 7. 1 minus 0 is 1. 0 minus -1 is 1. -1 minus -8 is 7. And -8 minus -27 is 19. So be careful with those double negatives when you're subtracting a negative number. So these are our first differences. Clearly they're different. Let's go to our second differences. And here we take our first differences and subtract them. 37 minus 19 is 18. 19 minus 7 is 12. 7 minus 1 is 6. 1 minus 1 is 0. 1 minus 7 is -6. And 7 minus 19 is -12. Again, nothing is matching. Keep going. We're going to do our third differences. 18 minus 12 is 6. 12 minus 6 is 6. 6 minus 0, 6. 0 minus -6 is 6. -6 minus -12 is 6. Our third differences are constant, and this equation or this function was y equals x to the power of 3. And the third differences were constant, and they were a constant value of 6. So now let's repeat the process for our next function. It's another cubic function, but this time we have a coefficient of -2 out front. So when I find my y value, I'll do -3 to the power of 3 is the same -27, but this time that y value that we originally had will get multiplied by -2 so that we have +54. And then -2 cubed is -8 times -2 is 16. Pause the video, finish with your y values, come back and check your work. Okay, so here are our y values. And now we can repeat the process with our first, second, third differences. So again, pause your video here and complete your finite differences until they become hopefully constant. And make sure you're being careful with your negatives and your signs in general. And here is my finite difference table. As you can see, our third differences were constant again. And just like the other function, this was a cubic function, and it was the third differences that were the same. So we'll keep that in mind and see what happens when we go to a function that's to the power of 4. So now we're going to start with x to the power of 4. So for our y values, -3 all to the power of 4 is +81. Remember, a negative number to an even exponent is positive. -2 to the power of 4 is 16. -1 to the power of 4 is 1. 0 to the power of 4 is 0. And then 1 to the power of 4 is 1. And then same numbers repeat again. And 4 to the power of 4 is 256. Now we can do our first differences. 256 minus 81 is 175. 81 minus 16 is 65. 16 minus 1 is 15. 1 minus 0 is 1. 0 minus 1 is negative 1. 1 minus 16 is negative 15. And 16 minus 81 is negative 65. Not the same, so let's go to our second differences. 175 subtract 65 is 110. 65 minus 15 is 50. 15 minus 1 is 14. 1 minus negative 1 is 2. Negative 1 minus negative 15 is 14. And negative 15 subtract negative 65, so that double negative again is positive 50. So I see some repetition in my values, but there's nothing constant here. So we keep going. 60, 36, 12, negative 12, negative 36. Still not the same. Again, 60 minus 36 is 24. 36 minus 12 is 24. 12 minus negative 12, 24. Negative 12 minus negative 36, 24. Now, if you make a silly mistake somewhere along the line, it is going to mess up your entire table. But in this case, we can see that our fourth differences were constant and our polynomial was to the power of 4. So let's go to our next table. We're creating the table of values for negative 2, x to the power of 4. So pause the video here, get your values, your y values, come back to check your work, and then we'll go to the finite differences. So hopefully you got these for your y values. And now, again, pause the video and complete all of your differences, and then we'll make some observations when you come back. All right, so here are our values. And as we can see, the fourth differences for this quartic function were the same, okay? So when making some observations here, what is true about the third differences of a cubic function? They're constant. What is true about the fourth differences of a quartic function? They're constant. So let's make a generalization. For a polynomial function of degree n, where n is a positive integer, the nth differences are the same or equal or constant. Okay? Now let's look at the actual value of those constants and how it might relate to the leading coefficient. So first of all, the difference between a positive leading coefficient and a negative leading coefficient. My third differences were positive, matching my positive leading coefficient. These third differences were negative, matching that negative leading coefficient. An exact same thing for the quartic function. Positive leading coefficient, positive constant fourth differences. Negative leading coefficient, negative fourth differences. So the sign of the leading coefficient related to the sign of the constant value is the same. So going back to our generalization, the nth differences have the same sign as the leading coefficient. Now let's look at the specific value of that fourth or third or whatever finite difference that is constant. This function here was cubic, and so was this one. This finite difference was constant at 6. This one at negative 12. Now if we compare 6 and negative 12, 6 was just multiplied by negative 2 to get to negative 12, which matches the leading coefficient. So something has to be multiplied by the leading coefficient to get to the third differences, or whatever is constant in that polynomial. So I'm going to look at the most basic cubic function, where could that 6 have come from? How could it relate to 3? Well, 6 is 3 times 2. 3 is that degree, and 2 is just a number less than 3. Maybe that's something. We'll see what happens with the fourth differences for the quartic function. And for this finite difference, it was still the same 3 times 2, but it was also multiplied by -2 because of that leading coefficient. Let's see what the scenario is for the fourth one to see if there's some sort of observation, conclusion we can make. The fourth differences for the basic quartic function, it was 24. Where does 24 come from? How does it relate to 4? Well, it would be 4 times 6. Where does 6 come from? Well, it's the same thing as with the cubic one. We said 6 was 3 times 2. It looks like I'm just multiplying the highest degree and then every number that's less than it. Every number that's less than 4 is 3, 2, 1. So I'm multiplying 4 by 3, 2, 1, and there's that 24. Whereas for the 48, I still have that 24, but it gets multiplied by the leading coefficient. And going back now to my other example, times 1 isn't going to change much. So your constant finite difference comes from the degree and the leading coefficient. If you take your degree and multiply it by every number that's less than it, and then by the leading coefficient, you have that constant finite difference. Now, what's an easier way to say multiply a number by every number that's less than it? A factorial. And this is what it looks like. So when you see n with this little exclamation mark, that's the same thing as saying I'm going to multiply n by the next number that's less than it, and by the next one, all the way until I get to 2 times 1. So if I was doing, for example, 6 factorial, that would mean 6 times 5 times 4 times 3 times 2 times 1. And that's exactly what we're doing here. So we're taking that degree and doing the n factorial, and then multiplying it by the leading coefficient. So let's write that out. So a times n factorial. So let's do one little example together based off of these observations. We're going to look at the first table of values, see what the degree of the polynomial is, the sign of the leading coefficient, and the value of the leading coefficient. And if I want to know the degree, I have to start with my finite differences. So I'm going to take the y values and subtract them. So that's 30, that's 14, 4, 0, 2, 10, and 24. Not the same for the first differences. So let's go to the second. 16, 10, 4, -2, -8, -14. The second differences are not the same either. I go again. 6, 6, 6. Okay, perfect. The third differences are the same. This must be cubic. So it's a degree of 3. Because the constant finite difference is positive, our leading coefficient would be positive as well. And then if I want to know my a value, I'm just going to go on the side here. Well, we know that our finite difference, so that constant value of 6, would be equal to the leading coefficient times that n factorial when n is the degree. Well, we know our degree. Our degree is 3. So the leading coefficient would get multiplied by 3 factorial. 3 factorial is 3 times 2 times 1, which is 6. So our a value must be 1 in this case, and positive 1. So there's a pretty full example of how we can use those observations to find some general information about our polynomial.